All right. So, in this last section here, 7.5, Applications for Science and Statistics, there are three basic areas that we're going to look at in using integrals to solve some problems. And the first kind is solving problems involving work, which is what we're going to talk about today. We're also going to talk about fluid pressure on a tank. And we'll also talk from statistics about the normal distribution. Okay, so it basically breaks down into those three categories. Okay, so let's start by talking about work. Those of you that are in or have been in physics, what is work defined as? Not to put you on the spot or anything, but do you remember the formula for it? Work equals what times what? Force times the distance. Yep. Good. Now here's the thing. Work is equal to force times the distance as long as the force is constant. It doesn't change. Okay? Because then it's just how far did we go, doing the same amount of force, or using the same amount of force, you just multiply the two numbers together, it's super easy. But as soon as that force becomes something that changes based on where you're at, then we got a problem. The old equation breaks down again. Okay? So, if we want to do it with a variable force, it becomes this. If that force is variable, if it's changing depending on where you are, okay, think of x as like if I'm walking along the x-axis, okay, and I'm carrying something that has some kind of weight to it, so it's got a force to it, and as I'm moving, okay, the weight of that thing is changing on me, okay? So dependent upon where I am in my journey as I'm walking along, that force is going to be changing on me. It's a function of x. Okay, it depends on where I'm at in my journey as to what the actual force is that I'm feeling. So it's an integral. So I've got to think about adding up a bunch of little instantaneous forces along my distance and then getting the work done that way. Okay? Usually, when you're talking about some kind of situation where you want to calculate work, this equation is just fine. Most things don't change their force as they move, okay? But if they do, we got to jump into this one, okay? So I'm going to give you guys kind of a classic calculus/physics problem that involves this type of thing, and it's called the leaky bucket problem. And as you can imagine, if I have a leaky bucket, the weight of what I am carrying in my leaky bucket as I move around is going to change, right? The more that leaks out, the lighter it becomes, the less force that I have from that bucket, the less work I'm doing, okay? But it's variable, though, okay? So it keeps changing throughout the situation. So we're going to have to, at some point, use this little integral definition for work to make it work. Okay, so here's the situation. So a leaky bucket weighs 10 newtons when empty. Oh, and by the way, we're going to switch back and forth between the metric system and the English system with force as well. Okay, so just so you guys are aware, I think we've all measured force at some point in the past, but just to review, a newton is a measure of force in the metric system. In the English system, we use pounds. So the weight, think of the weight of something, can be measured in either newtons or pounds. Okay, and that's a measure of force. Okay, so anyway, so this one's, it's a 10 Newton bucket. That's just the bucket though, okay? So as I move around with this bucket, if it's empty, is the force going to change? The bucket's the bucket. I'm not losing bucket. I'm losing what's in the bucket, right? So that part is going to stay consistent, okay? So keep that in mind as we move forward with this. So the leaky bucket, it weighs 10 newtons when empty. It is lifted 20 meters off the ground by a rope that weighs 0.3 newtons per meter. So every meter of rope is another 0.3 newtons added onto this now. So the bucket starts with 50 newtons of water. And is empty when it reaches the top. Oh, that got kind of cut off, sorry. So, yeah, so for those of you watching the video of this too, I apologize that it really got cut off a lot. So I'm going to read the whole paragraph again for everybody. So, a leaky bucket weighs 10 newtons when empty. It's lifted 20 meters off the ground by a rope that weighs 0.3 newtons per meter. The bucket starts with 50 newtons of water and is empty when it reaches the top. Okay, so the person that is lifting this bucket up to the top of wherever they're at is going to be really frustrated because their bucket full of water is now empty when it gets to the top. So how much work did this person essentially waste trying to do this? That's what we're going to figure out. So how much work is needed to lift this leaky bucket? Okay, well, really this problem breaks down into three pieces. There's how much work did this person need to use to lift the bucket? How much work did this person need to lift the rope, because the rope's part of it too? And how much work did this person need to lift the water that was in the bucket that was leaking out? Okay, so let's start with the easy one, the bucket. Because we already said the bucket is not going to change its weight as it goes up, right? The bucket's the bucket. And it weighs 10 newtons. So I don't even need calculus for this part. How much work is done lifting the bucket? Well, work we said was force times the distance. So what's the force of the bucket? I.e. the weight of the bucket. 10 newtons, okay. What was the distance that the bucket traveled? 20 meters. So the work done lifting just the bucket part of this would be 200 Newton meters. And yes, that is a unit. Guys in physics, have you heard that one before? Work is measured in Newton meters. That's in the English system. Okay. So, bucket, no problem. No calculus needed. Got it. Okay. The rope. All right, so here's the issue with the rope. As you're pulling this rope up, okay, you can think of it as you're kind of coiling the rope next to yourself as you're lifting it up. So as the rope coils next to you, are you lifting that anymore? No, right? So the weight of the rope as you're pulling the bucket up is doing what? It's changing. Changing how? Am I lifting more or lifting less as I pull the rope up? Less. When you get the whole rope out, when the bucket's all the way at the bottom, you get the weight of that entire rope. But by the time that bucket gets all the way to the top, you've got nothing left for the rope either. Okay? So it's kind of like you're losing rope as you pull it up. Okay? So the force that rope is exerting is changing as you bring it up. Okay? So then we got to consider a function then for the weight of the rope. Okay? So let's think of it like this. So weight at the bottom. How much does this rope weigh when it's all the way uncoiled? So take a look at what we have written for the information about the rope. And if it's all the way at the bottom, we've got 20 meters of rope. So how much does that rope weigh? 6 newtons? And how'd you come up with that?
I times or multiply that times how much the rope weighs by meter by 20 meters, which is how far you're lifting the bucket.
Yeah. So I've got 20 meters of rope. Every 1 meter of rope is 0.3 newtons. So 20 times 0.3, right? Should be 6 newtons then. Okay. So weight at the bottom, that's 6 newtons. So when it's at the bottom, so the x would be 0 down there. Okay? There's no distance has been traveled yet. I'm going to make x, think of x as kind of like a scale from x is 0 at the bottom, and then when it gets to the top, x is 20. Okay? So at the bottom, 6 newtons, that's when x is 0. Weight at the top. Okay, don't overthink it. How much does the rope weigh when it's all the way at the top? I have now coiled all the rope up next to me, right? 0. It's nothing. And this is when x equals 20. Okay? So, the equation for this rope I can get by thinking about this. Think of the weight of it as being kind of like the y, and where I'm at as being the x. And this is a linear relationship because the rate of change of the weight of the rope is constantly changing at the same rate as we bring it up. Because of the fact of this. Every meter it's 0.3 newtons. So I'm losing the same amount every meter that I coil up at the top. Okay? So can we create some kind of linear equation where y is 6 when x is 0 and y is 0 when x is 20? That's what we need to do. Basically, an equation of a line through 2 points. That's how we're going to develop that equation then. Okay? So let's start with what would be the slope of that line? Change in y over change in x. Or in this case, the change in the weight over the change in distance. Yeah. And that should match that up there, right? Makes sense, right? So we'll just think of it this way. Change of y over change of x. And this is the y again. Negative 0.3 would be that slope. Okay? And then what would be the y-intercept for this line then? What's the initial y? Or initial weight? 6, right? So the equation that I can use for the rope, so if I want to think of like, well, we'll just do it this way. So y equals negative 0.3x plus 6. So that's the function I need to integrate over then, from 0 to 20 of that. Okay. So the work done for the rope is going to be the integral from 0 to 20 of negative 0.3x plus 6 dx. Okay. What you're going to find with these, and with everything else that we do in this chapter, or in this section pretty much, is that the setup's the hard part. Okay? Doing the actual integration, piece of cake. It's not hard. Okay? It's going to usually be something linear, something easy that we can do. But it's getting the correct thing set up to begin with that's going to be the challenge. So, okay. So, you can do this by hand if you want to. That's fine. I think we end up with, what is this? Negative 3 over 20 x squared plus 6x. Taking that from 0 to 20. And that comes out to 60. All right. Like I said, you can do it all by hand if you want to, but not a big deal if you do it with a calculator. But it should be 60. Okay. So the bucket was 200. The rope was 60. So the amount of work done with the bucket and the rope, so far we've got 260 Newton meters. Now we've got to add to that how much is the water going to tack on to our total here. Okay. And we can approach the water the same way we did the rope. How much did the water weigh at the bottom? How much did the water weigh at the top? What's the slope? What's the y-intercept? Make another little linear equation just like we did for the rope. Do the integral over that, and we should be able to get another answer for that and then add it all together. Okay? So let's go investigate the water real quick. All right, so same kind of deal. What is the weight of the water? Or weight, sorry, at the bottom. So when the bucket's full, essentially, how much water do we have? It's in the problem. 50 newtons. Okay, and then the weight at the top. How much does the water weigh at the top? Nothing again, right? 0 newtons. Okay, so again, at the bottom, that's x equals 0. At the top, that's x equals 20. So can we do this same process here real quick then? What's the slope? So the change in y over change in x, again for this one. Except negative, right? Negative 2.5. Yep, because the change in the y is negative 50, and the change in the x is 20, right? So negative 50 over 20 would be negative 2.5. Then our equation for the water's force would be negative 2.5x plus 50, right? Because it started at 50. Okay. Same thing. The work is going to be the integral from 0 to 20 of that. So if we do our antiderivative work here, that's going to be, let's see, negative 2.5 divided by 2. So what did I have? Yeah, negative 5/4 x squared plus 50x. And that should come out to 500. All right, so question was, how much work work is needed to lift this leaky bucket. So water, bucket, rope, together, 760 Newton meters. All three of those pieces added together then. Okay, we just did it piecemeal. Put them all back together. So our total work, $760 Newton meters. Okay, so that's, like I said, kind of a classic problem involving work because you've got some variable forces going on there when things start changing weight as you move them around. Then you got to consider integration to help you do it with work. So we're going to talk tomorrow about, we're going to still talk some work again. We're going to talk about work done pumping. Okay, so if I'm going to be pumping some kind of a liquid out of a container, how much work is required for that? Because as the container drains, the amount of stuff in it is less and less and less and less. The force exerted by that stuff is less and less and less and less and less. So then the work needed to pump that stuff out is going to, the force that has, since it changes, then to calculate the work, we're going to have to use an integral for that too. So we're going to do that. We're also going to talk about this fluid force stuff. Okay. So if I put a fluid into some kind of a container, how much force is that fluid exerting on like the side of that container? Okay, but one thing that maybe you guys have studied in the past is as you go deeper into water, what happens to the force? It increases, right? That's why deep sea divers have to wear all that crazy equipment because the force on their bodies as they go deeper down in the water increases. So where you are in the tank, the force is something different. So the force is variable there again. So we're going to have to think about how much force total altogether. So we've got to chop it up into little bits, think about integration to do that again. And then we're going to finally look at the statistics stuff too using the normal distribution. So normal distribution, anybody that's taken stats or in stats right now? Yes? Okay. You guys have talked about the area under the bell curve, right? We're going to look at that too. So area under a curve, integration, right? Done area before. So there's a way to do that with integration too, to calculate area under a bell curve. So I'm going to stop for today because we only got a few minutes left. So. All right, guys, I think we're ready. Okay, so today we're going to talk about, at least to start with, work done pumping. So yesterday we talked about the concept of work kind of in general, and so today we're going to apply it to pumping a liquid out of a container and see how we can kind of use that same definition to attack these problems. So we started yesterday by talking about the fact that work equals force times a distance. Okay, and we're going to look at a situation where we're going to want to take some kind of a liquid and pump it up and out of a container. And so for us, we're going to be looking at work as being the force needed to pump, and then the distance is going to be the distance each piece needs to move. Okay, so it is still technically a force times a distance, but want to think of it kind of like in chunks. Okay, so we've got some kind of a container that we're going to break into all these little kind of slabs of liquid, and each one of those little slabs is going to have to move up and then out of the container. And so we want to think about what's the force needed to move each one of those little slabs up, and then what distance are they ultimately going to end up moving to come out of the container then. Okay, so we'll do an example of this. We'll start with a cylinder. Okay, and let's say this cylinder has some water in it, and it's only up to like a little ways up the container. Okay. So that would be the water sitting in that cylinder. And we're going to try and figure out what is the work needed to take all of that water and then pump it up and out of this container. So we put some thing here too. So the entire height of the cylinder is 10 feet. The height of the water is 8 feet. I know this is really not to scale, but it's just how I drew it. And the radius of the container is 4 feet. So the question would go something like this. The density of water is 62.4 pounds per cubic foot. So yesterday we were working in the metric system, talking newtons and all of that. So today we're going to be in the English system, talking pounds and feet and stuff like that. So 62.4 pounds per cubic foot. Okay. So notice how that is a force over a volume, right? That's important. Okay. So the density is measured as a force over the volume. So how much water or how much work is needed to pump all of the water over the brim? So, like I talked about before, we're going to have to think of this as like this water has been divvied up into all these little tiny slabs, okay? Because each one of those slabs, it's going to take a different amount of work to get it to pump up and out, okay? Depending on how far down the slab is that we're pumping. The slab at the very bottom of the container is going to take more work to pump it all the way up and out than the very top one is, right? Does that make sense? So it's not all the same. You can't just figure it out for one and then multiply by however many you have or that sort of thing. Because each one of those, depending on its depth, is going to take a little bit less or a little bit more work. So we're going to have to kind of come up with a variable and work that way with it. Okay? So, so let's just consider like one of these infinitely thin little slabs that would be on here. So just think of like, yeah, like a little disc. Of water. And we're going to work on pumping that thing out of there. Okay, so like we'll just think of one in general, and then we'll just apply that to all of them that we have there. Okay, so so the first thing we need to do is we need to figure out, okay, so what is delta V, the change in volume of one of these little slabs? Okay, and so each one of those little slabs, it is essentially just an infinitely thin cylinder, right? And each one of those little cylinders, they have the same exact size base on them, and they're circles, okay? So pi times 4 squared, that's the circle, times their height. Well, because they're infinitely thin, we got to go with delta y instead of just y. We don't know, but it's supposed to be this like infinitely thin little thing. So the change in volume that we're getting is pi r squared, the area of the circle, and then delta y, which is the height of each one of those little slabs. Okay? And each one of these little delta v's is what we want to try and pump in and out of this thing. Okay? So, pulling that all together, delta V is 16 pi delta Y feet cubed, because that's a volume, right? Okay, so in general, in this one we're using a cylinder to pump things in and out of, okay? You might have something that's shaped like a square or whatever. So you have to think about that cross-section again, kind of an idea. So as I cross-section this container, what kind of a shape am I creating in each one of these little slabs that I'm trying to pump out of this thing? Okay, so in this case, I'm dealing with circle times the height. Or if it was a square, you'd find the area of the square multiplied by delta y, or whatever it is, okay? So it all depends on the container as to what exactly you're going to do here, but your first step is always to get this little delta V and get a little formula for that with delta Y in the mix. Okay, so we've got that. Then we can use that to find the force. Okay, because remember, we talked about they give you the density of water, which is a force divided by volume. And hey, guess what? This is a volume. So we can use those two pieces of information together to get a formula for the force that we want. Okay? And we want force as a function of y. And y is the height, again, because like I said, it depends on how high up this thing is as to how much force it's going to take to pump it out of there. So our little equation, f of y, is going to be determined by the density times the volume. Because the units just kind of take care of that for us. So we've got 62.4 pounds per cubic foot multiplied by this 16 pi delta y cubic feet. So cubic feet cancels, we're left with pounds, which is a force, so we're good to go. And then multiplying that all together, we end up with 998.4 pi delta y pounds. Okay, so going back real quick to where we started with this thing, if we take a look, we said the work is going to be force needed to pump multiplied by the distance each piece needs to move. We've taken care of this part right now. Force needed to pump, we got it. It's right here. 998.4 pi delta y. That's the force. Now the only thing we need to figure out is the distance that it needs to move. Okay? So if we go back to this original picture here, okay? So consider for a second where this slab is at. This y that we've been using in here, that's how high up that slab is from the ground. So this distance here, so from this to that, that's y. The distance needed to pump, however, would be wherever that slab is up to the top of the container. So if this is y, what is this distance up here? 10 minus y. Right. So however high up the slab is, 10 minus that is how much further it's got to go to pump up and out of the top of the container. Okay? So our work equation then, or at least our delta W, is going to be force needed to pump, just got that, 998.4 pi delta y, and then the distance that it needs to go times 10 minus y. But these little slabs are infinitely thin, right? So it's not delta W. You can kind of think of it as like a dW or whatever. And we talked about this yesterday, where this then just converts into an integral because we got to add up all those slabs, pump them all out of the thing. So the work needed is going to be the integral of this, 998.4 pi 10 minus y, and then instead of delta y, we'll just put our little dy on the end of it. And then becomes, well, what are the limits on the integral, though? From what to what are we pumping? And remember, the variable we're using in this thing is y. So if we look back at the container, think about how we labeled this thing. What do you suppose are going to be my limits on my integral? What exactly am I pumping from what to what up out of this container? Or, well, 0 to 8, but yeah, exactly. Because this chunk of water is what I'm pumping, right? And think about all these little slabs that I'm breaking it into, okay? So all those little slabs are from what to what? 0 to 8, right? The bottom of the water to the top of the water. That's the stuff I'm partitioning. That's what I'm pumping out. So my limits have to be 8. Yep. So now I've gone through all that process of setting this thing up. Now I've finally got an integral that I can use to calculate the work needed to pump. Okay? So 0 to 8, 998.4 pi times 10 minus y. This you could do by hand very easily, but just for the sake of time, why don't you go ahead and just punch that into your calculator. Let's see what we get. And this should be a very large number when you're done. Like in the hundreds of thousands, if we did it right. So, you got it. So 150,555. So here's the question. 50,555 what? What did we use this time? David had it. What is it? Foot pounds. It's not Newton meters. Remember, we're in the English system this time. So now we've got, instead of Newton meters, foot pounds. I guess, yeah, it's kind of weird how they kind of switch. But, yeah, anyway. So if you're in the English system, work is measured in foot pounds. If you're in the metric system, work is measured in Newton meters. Okay, so does that process make sense? More or less? The only thing that's really going to change in the other problems that you might have involving this stuff is the density of the liquid involved. I think there's one in your homework where it's like olive oil or something instead of water or whatever. So they'll tell you what that is, though. So there's a different density, perhaps, and the shape of the container might be something different. So where we'd had little, cylinders that we had to pump out of this thing, maybe you have like little square prisms or triangular prisms or something else, some other kind of shape. But it's something from geometry. You should be able to come up with the formula for the area and then go from there. So that's work done pumping. Okay, I don't want to do more than one example because they take forever. The next thing we're going to look at is fluid pressure. Okay, so with fluid pressure, for this one, the answer is going to be a force. So we're not talking work anymore, okay? So it's not force over a distance. It's just simply how much force is being exerted on one side of a container or on the bottom of a container or something like that, okay? So here's generally the idea. The force created by pressure is the integral of the pressure times the area. Okay, and this area is going to be some small strip on a side. Okay, so this is just if we're talking about the fluid pressure on the side of a container, which often is what we're talking about. Okay, so this will make a little bit more sense when you kind of see what we're doing here. So I'm going to start with, we'll just do a box, okay, and it's got some liquid sitting in it. Bless you. All right. So let's say that we've got, we'll go with water again. So a box is filled with water. What is the fluid pressure acting on one side of this box? Okay, so like this is the type of question that engineers are interested in. If you were like, let's say you were building a dam or something that needed to hold X cubic feet of water or whatever, so you need to make sure the materials that you're using are strong enough to withstand a certain amount of force that would be exerted by the water on that container, that sort of thing. Okay. Even something as silly as those little milk cartons that you buy for little kids, that sort of thing, just like the cardboard that's used on those. Are they going to hold up? That sort of thing. So this kind of thing actually does get used quite a bit. The tricky part is, though, again, the deeper you go, the more pressure you're going to have, right? Pressure is not constant. Pressure is less at the top than it is at the bottom. And so to find the fluid pressure on one side of this box can be tricky because you've got to kind of add up all these little pressures all the way down to the bottom that are all different. So hence integration, we got to go through and add up all these little infinitely thin strips of pressure this time rather than thinking about it like work. Okay, so this box, say it is 10 foot by 10 foot by 5 foot. And let's say we're just looking at this side over here. We want to know how much fluid pressure is acting on that side over there. Okay. Well, I talked about this idea of we have to think of it like in these little infinitely thin strips. Okay. So the area over there, it's going to be some small strip on a side, right? So think about okay, so we've got like this little strip, and there's like, it's like I said before, it's infinitely thin, and we've got all of these added up all the way through this thing. So that little strip, we want to think about what is its area. Okay, so think of it as a rectangle, even though it's technically infinitely thin and not a rectangle, but rectangle base times height, right? So what is the base of this rectangle? How wide is it? 10, okay. And the height of it, think back to the last one we did. What did we talk about as the height for one of these infinitely thin little strips? What did we use in the last problem? Delta y. So that's what we're going to use again. So the area of that strip is 10 delta y. Okay. And we said the integral is pressure times. So we've got essentially the area of that strip. Okay. So it would be 10 delta y. It's a matter of what is the pressure, because we need to do pressure times area. So pressure is defined as weight density times the height. So the weight density, we actually, in the last problem we just called it density. It's the same thing. So what is the weight density or just density of water? What did we have in the last problem? What was that number we used? Or 62.4, right?
Yeah.
Should have been? Okay. Yep. So our pressure here then, we've got 62.4 pounds per cubic foot. Okay, because we said we were using water, right? So again, we're going to use that same weight density. If it's some other different fluid, they'll tell you what it is, so you can just use that number instead. And the height of this thing, well, the height is variable, so we're going to just call it y. Okay, because we don't know where it's at. So like that height would be referring to like that. That's y. The strip is y up from the bottom. Okay, so if we want to do now the fluid pressure, the force that we're getting from that, we've got really everything we need. We've got the pressure, we've got the area, and we can go to work on this now. So we'd have the integral of the pressure, which is 62.4 y, and then times the area, which is 10. Now it was delta y, but we can change that now into a dy because we're doing the integral case. So times 10 dy. And then the question becomes again, what are going to be the limits on my integral? So take a look at that picture, and from what to what are we using to find the pressure? 0 to 5, right. Now we're partitioning like that side of the cube or that side of the box from a height of 0 up to a height of 5. So our limits are 0 to 5. Okay. So again, the setup's the difficult part. The actual integration of this is pretty simple. 62.4 times 10, we've got 624, which I can bring outside the integral. 0 to 5 y dy. The antiderivative of y. So what is it, Rachel? Okay. So 624 times 1/2 y squared from 0 to 5. So plugging in a 0 will just get you 0 again, right? So if I plug in the 5, that should be my answer. So 624 times 1/2 5 squared. So that is 7,800. 7,800 what? We're talking force, and we're in the English system this time. So how do we measure force in the English system? Pounds, right? There's 100 pounds of force acting on that side of the container. All right. So we'll do one more. And we'll use this same box for this. So this time, instead of one side of the box, I want to know what's the total force acting on the bottom 1 foot strip. Because usually, if we're building some kind of like industrial-sized big container for something, it's that very bottom that we're concerned with, right? Because that's where all the big force is going to happen. So let's figure out how much force is acting on that bottom 1 foot strip. So, if it needed to be reinforced or something like that, they would know how much materials or what they would need to do to ensure that that bottom part was actually holding up the way it was supposed to. Okay? So I'm going to draw this picture again. And actually, you know what? In thinking about this problem, I need to make a quick correction. It's not going to change our answer to the last one, but I need to make a quick correction here. This little y, that's not on the right spot. I screwed that up. The y is actually from here to here. In this one, think of the y as like the depth, okay? And in this little part, where was it? Where we did the weight density times the height, the pressure. Remember how I said the pressure gets larger as you go down, right? So if y is larger, you should have more pressure, right? Not less pressure. So if we think of y as starting from the top, and as you go down, pressure increases, right? So think of y as a depth, not as a height so much. Does that make sense? Because if we increase the y right here, what's going to happen to the overall value of this? If I keep multiplying it by 62.4, it's going to increase, right? So as y increases, the pressure increases. That has to be the case, right? So the further down we go, the more pressure we should have, okay? That's going to be really important in the way we set this one up, in how you interpret this other one if you don't think about it that way. So y, and in fact, you know what? If you even want to take this part here where we wrote the word height and change it to depth, I think that's going to be more helpful. Okay, so it's not so much a height as it is a depth. Okay, so let's go back to this then. So what is the total force acting on the bottom 1 foot strip? So we're looking at this whole piece here on the bottom of that cube. All right, so we still got, this is 10 feet, this is 10 feet. This box here at the top of it's 5, but it's not real important that we worry about the fact that it's 5 anymore because we're only looking at the bottom little 1 foot. So this is 1 foot. Okay, so same kind of thing. We're going to start with the area of this whole strip, okay? Now before, we talked about area as being this little infinitely thin side here, or this little infinitely small strip, okay? With this one, it's a little confusing because that strip is not infinitely thin. However, we still need to partition it into a bunch of infinitely thin little strips that go all the way around the box, okay? So, looking at, like, consider this as like one of the little strip pieces that we need to take off and add up, okay? So that thing, that infinitely thin little strip that goes all the way around, this box, okay, its area. So if I were to take it and peel it off and make it one big long strip, how long would it be? How many feet long would that strip be? Okay. And what would be the thickness of that strip again? If it's infinitely thin, what do we use as the thickness of the strip? That delta y. Yeah. Okay, because it's 10, 10, 10, 10, and then the little thickness of it is delta y. Okay, so that's what we got to go with then. It's 40 delta y is the area of that, what we need. Okay, pressure should work pretty much the same way this time. It is the weight density times the depth, which hasn't changed, right? So we can use 62.4 is the weight density of water times the depth. Still use y because that's still variable, right? Even though we're doing the bottom 1 foot strip, it's still variable of what that depth is. And so we can still go with 62.4 y. And now we've got what we need to go plug this thing in and create an integral for the force acting on it. So we got 62.4 y. That's the pressure times the area, 40 dy. But what's going to be, or what are going to be the limits on that integral then? 4 to 5, which is why I talked about this over here. Think about it for just a second. Let's go back to this box right here. Y is measuring a depth, right? If the height of the box full of water is 5 feet tall, the depths we are looking at is a depth of 4 to a depth of 5. Does that make sense? Okay, if it's measuring depth, it's from a depth of 4 to a depth of 5. So those are the limits. This is the one place where it's really easy to make a mistake. In fact, one year when I was lecturing on this, I did it 0 to 1 and got the wrong answer and then couldn't figure it out for like 2 days. So, okay, 4 to 5, not 0 to 1.
Why when we were doing areas, did we do like the circumference?
Because this time we're not talking about the pressure acting on just one side. It's all 4 sides all the way around. So we have to go with that whole strip all the way around, not just on one side of the box. Yeah. So, okay. That's the hard part, but the integration's super simple. So you just multiply 62.4 times 40. And that gets us, I think, 2496. And integral from 4 to 5 of y dy. And so that leaves us with 2496 times 1/2 y squared, going from 4 to 5. And so 1/2 times that is going to be 1248. And then we got to plug in a 4, so 4 squared minus 4 squared. That's going to be 25 minus 16, so that's 9. So 1248 times 9. We have 11,232 pounds of force. So that's interesting. The bottom 1 foot strip has actually a considerably more amount of force acting on it than the entire one side of the box does. Because the last one we did was the side of the box. We got 7,800 pounds. This is just that bottom 1 foot strip, and we get 11,232 pounds. So depth makes a huge difference. So, okay. That's kind of fluid pressure in a nutshell. Okay? The last thing we're going to do, and actually this one is quite a bit easier than the rest of these. I know this stuff is a little bit intense with all the setup and everything. But doing the statistics side of thing here, there's just a nice formula. If you have a little bit of information, you can just plug in and go. It's just a matter of being careful when you put it in your calculator. Whoops. So area under a bell curve. All right, so I guess I do probably need to kind of brush a little bit of how a bell curve is used. So there's this thing called a normal curve, which is the other name for a bell curve. So if the data from something, and let's talk test scores, because that's always the easiest thing for you guys, I think, to latch onto with this stuff. So let's say that we had a bunch of test scores, and I normalized the data. So whatever was the kind of the middle or most common score, that I put right in the middle. That's my average, okay? And then from there, so I made it so most of the people are clustered around the average. And then as you go, people that did better, there's fewer and fewer people that did better than the average, and there's fewer and fewer people that did worse than the average the further you go out. So if you organize the data that way, it makes this nice looking bell curve. It's nice and curved, and it just levels off on either end, okay? And technically, even though like if you're thinking test scores, you can only go up to 100, and you can only go down to 0, but technically, a bell curve in general will continue going out to negative infinity and positive infinity, and it'll just keep getting smaller and smaller and smaller and smaller as it goes. Okay. That we're using has been normalized, has been made into the shape of a bell curve, so that the average is right in the middle, and it kind of slowly drifts off on either side. If we have data set up like that, then we can answer some questions about, like, okay, what percent of the class scored between this amount and that amount, and the area under that curve will tell what that percentage is, okay? Because the way that a bell curve is set up, the area underneath it is exactly 1. So if you find an area of one little chunk of it, and let's say you get like 0.65 for the area of this one piece of it that you're looking at, well, then you can know for certain that 65% of the data is in that portion. Or if you do the area under the curve and you get 0.8, then you know that 80% of the data is in that little piece of it. Okay, so it's wherever you're partitioning it, then you can work on or a percentage of the total based on how much of the area you have in relationship to 1, because the whole area is 1. Okay? So, again, a few extra little notation things here. This is not me trying to make a U anymore. This is actually mu. Okay? And that is the symbol that gets used for the mean, or the average. Okay? And the average is always the peak of the curve. All right, and there's another number that we use to describe data when it's been normalized. That's standard deviation. Anybody taking stats? No standard deviation? Yeah, okay. So standard deviation it's a lot more to it, and you guys have probably studied this in a lot more detail than I'm going to try and talk about right now today. But standard deviation basically is a number that describes how spread out the data is. So if you have a small standard deviation, that means that all of the other data is really packed in tight to the mean. So you're going to have a bell curve that is very skinny and tall. Still has an area of 1. That doesn't change. But everything's been kind of smashed in a little bit more. Okay? If you have a very large standard deviation, that means that the data is very spread out. And you're going to have a short, squatty, fat curve. Okay? So, but the way standard deviation works, though, whatever that number is, if I go that far above the mean and that far below the mean, one standard deviation, always, 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 one standard deviation is going to give you 68% of the data. Okay, and this is the symbol we use for standard deviation. So if you go 2 standard deviations out, so from here to here, now we've got even more of this thing. And 2 standard deviations will always get you 95% of the data. And standard deviations, this is getting a little... Oh. Just keep rolling out, just keep rolling out. So, standard deviation, you have like 99.7%. Okay, so these 3 numbers, those of you that are in stats have probably heard of this before. It's the 68, 95, 99.7 rule that you can just quickly apply to however many standard deviations you have. And you can keep going out, 4, 5, 6, 7 standard deviations, whatever. But it just keeps getting closer and closer and closer to 1 as you go. Now, if you don't have calculus to help you, you're kind of stuck into this, is it 68%? Is it 95%? Is it 99.7%? But we have a formula that I can give you. If I give you the average and I give you the standard deviation, you can tell me the size of any portion of this thing underneath. Okay? So that integral that we would take the integral of is called the probability density function. Okay? And it looks like this. And don't ask me where this comes from because I have no idea how they got this. But all I know is that I've used it before and it works. People that are much better at statistics came up with this than me. Okay, so like I said, the trickiest part of this is gonna be just making sure that you put everything in correctly. And if you want to find the area under the curve, it is simply the integral. Let's do a real quick example of this then. The average on a test was, I don't know, let's say an 82% with a standard deviation of 30%. What percentage of students earned a B of some sort? Okay. So, let's first come up with the probability density function for this situation, okay? What's our mu for this? What's the mean? $82, okay. What's the standard deviation? Or you can just use 5 in this case, because if we're going to use the average as 82 instead of 0.82, we can use the standard deviation as 5 instead of 0.05. But either way is fine. It'll work out just fine either way. You just got to make sure you stay consistent with it. Okay, so our f of x then for this, we've got 1 divided by 5 square root of 2 pi e to the negative x minus 82 squared over 2 times 5 squared. All right, so let's clean that up a little bit. So f of x is, let's figure out what is that 1 over 5 square root of 2 pi real quick. Okay, so we got 0.079, we'll go 798. We round that off just a little bit. Then e, now this we got to keep the same, negative x minus 82 squared, and then that over 2 times 5 squared, 50. And we want to do the integral of this, right? Because this is the equation of the bell curve that fits this situation, okay? So we want the area under this bell curve, but from what to what? We want to know within what 2 scores. If they get a b of some sort, it's between what and what? 80 and 90, right? And some of you might be thinking, well, why don't we do 80 to 89? Because isn't 90 an A? But we want to do 90. Why? We want to go up to that, because what's an 89.9? Still a B plus, technically, okay? If we don't consider rounding and all that business, it's still technically a B plus. So we're going to do the integral from 80 to 90 of this 0.0798 e to the negative x minus 82 squared over 50 dx. All right, punch it up. Be careful with the exponents. Parentheses are your friend. Okay, I'll do the same thing. I'll show you how I did it too. See if we match how we typed it in here. Here's what I got. See if it matches yours. I got about 60%. Sound right? Okay, so like I said, parentheses just to be safe. So e to the parenthesis negative parenthesis x minus 82 parenthesis squared over 50 parenthesis. Then you're good. X 80, 90. It's about 60%. Okay, so that's the kind of thing you're going to be doing with this, okay? From some number to some number with that formula with the average and the standard deviation plugged in. Now, there's some little wrinkles they can do with this, and we got a little bit of time, so I want to talk about those wrinkles, and then I'm going to be done. So what if I wanted to know, let's do the same situation, but what percentage scored over a 60%. So I want to know like what percent of my class passed, essentially. Even though we're talking test scores, I guess you could put in 100 up here and okay, if there wasn't any extra credit or whatever. But just in general, though, whatever it is you're talking about, to answer a question like this, what would the upper limit really have to be? Because the bell curve just keeps going. Really high, like how high can you go? What's all the way? Infinity, right? Technically, you'd have to have a little infinity up here. We can't do that. You'll learn how to do that in Chapter 8, actually, but you can't do that right now. So, we can't go to infinity, but the bell curve is nice and perfectly symmetric. It has the same shape or the same size on one side of the average as it does the other. So what percentage of the data is above the average? $50, right? And what percentage of the data is below the average? 50. So do I really need to go to infinity? No, because I know from here all the way out is 50%. I want to know how much is greater than 60. 60 is lower than the average, right? So if I go 60 to the average, get a number for that, and then I'm going to add that to what? 50, because from the average all the way is 50, then I got this little chunk. I find out whatever that is, add it to 50%. That's our answer, right? So that's what we're going to do. We're actually going to do an integral of this thing just from 60 to 82 and add it to 0.5. And that'll be our answer then. So if you want to go back to your calculator to do this, you guys all know how to do that second entry so you don't have to type it all in again. Just keep hitting second and enter until you see that integral, and then all you got to do is go back in and change the limits. We want it to be 60 to 82. Huh, that's interesting. So, what do you get from this one? About 0.5, yeah. So, that means that about half the students scored between a 60 and an 82, plus the other half that we know is from 82 to infinity. So, pretty much everybody passed this test then, with a standard deviation of 5%. That's such a small standard deviation. I mean, there's a teeny tiny amount that is less than 60, but it's so negligible that your calculator can't even catch the decimal. So we know from 82 and up is 0.5. So 0.5 plus 0.5, we've got essentially, though it technically is like slightly less, essentially 100%. Everybody passed the test. Okay, so that's the one little thing I wanted to caution you about. If it asks a question like that, where it's, well, what's the percentage or what's the probability or whatever that it is this or above, or they might even do this number or below, then you want to use the fact that half the bell curve is 50% to help you out. Okay? So, okay, I think I've given you guys plenty to chew on there. So, I'm going to stop, and you guys can start looking at your course site stuff, what we've got set up for this section. All of it will be due on Monday. Okay, tomorrow's your online day to work through it, and then on Monday, we'll come back and talk about it.